Alright, hello. We're going to continue our discussion of vibrations and waves and look at section 2, which involves properties of waves. So last time we talked about springs and how we relate those to waves, and then we're going to talk about some wave properties. Okay, so both waves and particles carry energy, and we know this from chemistry, but we're specifically going to talk mainly about waves for physics. So a wave is a disturbance that carries energy through matter and space. So think about sound waves or microwaves or thermal, like energy waves. All of that carries energy through matter and space. And there are many types of waves. We're going to talk about three main types involved in mechanical waves. So mechanical waves require a medium, whether it be water, air, a rope, a spring. We need something through which to pass the waves. And these can serve as models for waves that also can't be directly observed. So if you think about a rope, we're going to create this wave that now we can directly observe it because we're doing it through a rope. And there are three main types of mechanical waves: transverse wave, a longitudinal wave, and a surface wave. So let's talk about transverse waves. These are ones that vibrate perpendicular to the direction of the wave's motion. So if the wave is moving this direction, the waves are vibrating this direction. A wave pulse is a single bump or disturbance that travels through a medium. So for example, let's say you had this lake that was very calm and looked like glass, and you stuck your finger on it. Now you would cause this ripple effect. So that would be a wave pulse. A periodic wave is generated if a wave moves up and down at the same rate. And so we're going to talk a little bit more about periodic waves. Longitudinal waves are where the disturbance is in the same direction or parallel to the direction of the wave's motion. So if the wave is moving this direction, then the disturbance is also this direction. Think of like a slinky. If you were pushing it back and forth, that would be in the direction of the disturbance. Some other examples of this are sound waves and fluids behave as longitudinal waves. So let's look at the difference between transverse and longitudinal. So transverse, your hand motion is going up and down, and here your wave direction is horizontal, and so this is where we get perpendicular. And to have a periodic wave, do you see how it's repeating over and over? This is what we would be looking at as a periodic wave. Longitudinal waves, my hand is moving left and right, and my wave direction is also left to right, and so this is where it would be parallel, me giving it a longitudinal wave. Our third type of waves are surface waves. These have characteristics of transverse and longitudinal waves both. And so the particles move in a direction that is both parallel and perpendicular to the direction of the wave motion. Okay, so we've talked about three different types, and now we want to talk about what are the different quantities we can use to measure a wave. Well, there are lots of different ways to describe or measure a wave, including speed, amplitude, wavelength, phase, period, and frequency. So we're going to talk about each of those. So let's look at speed. This is the same as any other speed when we talked about speed is displacement over time for a person or any object. So we have that speed or velocity is delta d, which is the displacement of the wave peak. So you pick one point on the wave and you follow it. And delta t is the time interval that it takes to do that displacement. For most waves, the speed depends only on the medium through which the waves move, and we're going to get more into that later. The second thing that you can measure on a wave is amplitude. This is the maximum displacement of a wave from its position of rest or equilibrium. So if you remember from section 1, we were talking about the guitar string and the simple harmonic motion. So if we have our wave, then if we call this our equilibrium, then this displacement is going to be our amplitude. So you can see we can have our amplitude above and below the equilibrium. Amplitude depends on how the wave is generated, not on its speed. So speed and amplitude are going to be different. And so just because something moves fast doesn't mean that it has a large amplitude. Waves with larger amplitudes, however, do transfer more energy, and so there is a relationship between amplitude and energy. Doubling the amplitude will increase the amount of energy by about 4. So I would say it's definitely a positive or direct relationship, but not, I guess what I would say, linear. So the rate at which energy is transferred is also proportional to the amplitude squared, and that's where we're getting the doubling the amplitude increases the energy by 4. The third thing we can measure is wavelength. And so if we look at our wave, this would be one cycle of a wave. And so this would be wavelength. So if I draw a couple more in, of course, they're extremely even. The trough is the low point of the wave, and the crest is the high point of the wave. And so the wavelength is the shortest distance between points where the wave pattern repeats. And so usually we measure this from crest to crest. You could also measure it from trough to trough. You can measure it from equilibrium point to equilibrium point, but that one can get tricky because you could maybe mix up and use that one instead. So the traditional way we measure is crest to crest. And the symbol we use for wavelength is the Greek symbol lambda. Another characteristic of waves that we can measure is phase. So any 2 points on a wave that are 1 or more wavelengths apart are in phase. And so they have the same displacement from equilibrium and the same velocity. So we would say that the crest and the trough are 180 degrees out of phase with each other. If we looked at our example of the wave again, we would say that maybe this point and this point are in phase because they're a whole wavelength apart. We could also continue that and say that this point and this point are in phase because now they're 2 wavelengths apart. Alright, so the last 2 things that we can measure are period and frequency. This applies only to periodic waves. And I think the classroom lights just turned off. One second. Okay. So the period, or capital T, is the time it takes for the motion of the source of the wave to complete one cycle. Okay, so that one cycle of a wave is the amount of time, that's specifically the period. And then the frequency, or F, is the number of complete oscillations the wave makes each second. So it's basically the rate at which the wave travels, and it's per a period of time. We could say 1 second, but you could count any amount of time. You would just have to take it divided by that time. So frequency is equal to 1 over the period, and then if we take frequency and combine it with our speed or our velocity, wavelength is equal to velocity over frequency. And so you can use these 2 equations to solve for some of your variables. So if you don't have these on your note card, this would be a good idea. Okay, so let's kind of review a couple of the things, and we've done a lot of pictures already, but wavelength is from the point on one wave to the point on an additional wave. You have amplitude is the distance vertically from equilibrium. We've got peak, or we would call this the crest. Okay, and so the more waves that pass by in a certain amount of time, the higher the frequency. Okay, so these are the examples that we're going to do together in class, and then here's the homework along with the answers. Have a good day.